When you look up at the night sky, what do you see? Tiny points of light scattered across a vast, dark canvas. It all seems so peaceful, so distant. But what if that whole cosmic panorama, everything you see and everything you don't, is just the interior of something even grander and stranger? What if our entire universe, with its billions of galaxies and countless stars, is enclosed within the shadowy confines of a black hole? It sounds like something ripped from the pages of a science fiction novel, a plot twist for a cosmic movie. But in the world of theoretical physics, this isn't just a fantasy. It's a serious, mind-bending possibility that scientists explore with the rigorous tools of mathematics and the laws of physics. Before we can imagine our universe inside a black hole, we first need a clear picture of what a black hole actually is. Forget the pop culture image of a cosmic vacuum cleaner sucking everything up. The reality is more subtle and much weirder. Albert Einstein taught us to think of space and time not as a fixed, empty background, but as a single, flexible fabric: space-time. Imagine this fabric is a giant, stretchy rubber sheet. Now place a bowling ball on it. The sheet bends and sags under the weight. That dip in the fabric is what we feel as gravity. A planet, a star, your own body creates a small dip in the fabric of space-time. Now, imagine an object so incredibly dense that its weight creates a dip that is bottomless. Imagine an object that warps the space-time sheet so severely that it forms an infinitely deep well. That is a black hole. So how do we get from a single collapsed star to an entire universe? The idea hinges on the mathematical descriptions of black holes and the Big Bang. The equations that describe the singularity at the center of a black hole look remarkably similar to the equations that describe the singularity at the beginning of our universe, the Big Bang. In both scenarios, you have a point of infinite density and temperature where our current laws of physics break down. This mathematical parallel led some physicists, like Nikodem Poplawski, to ask a provocative question. Are these two different phenomena, or are they two sides of the same cosmic coin? Could the Big Bang have been the formation of a black hole? Let's follow this line of thinking step by step. Imagine a vast, older universe, a parent universe. In this parent universe, a massive star runs out of fuel and collapses under its own immense gravity. As it collapses, it forms a black hole. According to some theoretical models, the matter that falls into the black hole doesn't just get crushed into an infinitely small point. Instead, the incredible energy and density could trigger a rebound. The matter might bounce back, but it can't escape back into the parent universe because it's trapped behind the event horizon. So where does it go? It expands into a new region of space-time, creating a child universe within the black hole. From the inside, that rebound looks like a Big Bang, a hot, dense state rapidly expanding and cooling, eventually forming galaxies, stars, and planets. While direct proof is out of reach, a few intriguing observations and theoretical arguments lend some support to this cosmic nesting doll idea. The first clue is the flatness problem of our universe. Observations show that the geometry of our universe is remarkably flat on large scales. If you draw a giant triangle between three distant galaxies, its angles would add up to 180 degrees, just like on a flat sheet of paper. This is strange, because according to general relativity, any initial curvature at the Big Bang should have been magnified over 13.8 billion years. For our universe to be so flat today, its initial state must have been fine-tuned to an absurdly precise degree. The black hole model offers a natural explanation. The dynamics of gravitational collapse, the subsequent rebound, naturally lead to a universe that is spatially flat. A second reason to consider this idea is the universe's arrow of time. Why does time in our universe seem to flow in only one direction, from the past to the future? Why does entropy, or disorder, always increase? In the context of a parent universe, the direction of time inside the child universe could be inherited from the gravitational collapse that formed it. The flow of matter falling into the black hole sets a specific temporal direction. For the new universe born inside, this direction becomes its fundamental arrow of time. The expansion from the bounce is intrinsically tied to a forward march of time, providing a physical reason for the asymmetry we experience every moment of our lives. The third clue is more theoretical and relates to the nature of dark energy. Dark energy is the mysterious force that is causing the expansion of our universe to accelerate. Some versions of the black hole universe model suggest that interactions with the parent universe or the geometry of the black hole's interior itself could manifest as an effect that we perceive as dark energy. For instance, the rotation of the parent black hole could impart a kind of outward-pushing force on the space-time within it. What we measure as a baffling cosmic acceleration could be a subtle inherited artifact from the dynamics of the larger cosmos our universe resides in. These clues don't constitute proof, of course. They are more like tantalizing hints or circumstantial evidence. They show that the universe in a black hole hypothesis isn't just a wild guess. It's an idea that can potentially solve some long-standing cosmological puzzles in an elegant way. It connects the properties of our universe, its flatness, its arrow of time, its accelerating expansion, to a single plausible origin event. It takes what seem like arbitrary, fine-tuned initial conditions and reframes them as the natural outcomes of a physical process that may be common throughout the cosmos. It's this problem-solving potential that keeps the idea on the drawing board for theoretical physicists. Despite its elegance, the idea that we live inside a black hole faces significant skepticism from many scientists, and for good reason. The first and most powerful objection is the lack of unique, testable predictions. A good scientific theory must do more than just explain what we already know. It must make specific predictions about things we haven't observed yet. Those predictions let us test theories against reality. While the black hole model can explain things like the flatness of the universe, so can other theories. Most notably, the theory of cosmic inflation. Inflation proposes a period of hyper-fast expansion in the first fraction of a second after the Big Bang. Inflation's predictions have been borne out by observations, giving it a stronger scientific footing. By contrast, the black hole model has yet to produce a smoking gun prediction. A second major problem is the sheer scale required. The black hole that would contain our observable universe would have to be incomprehensibly massive and have an event horizon on the scale of our cosmic horizon. Its mass would need to be roughly the total mass of our universe, and its event horizon would be billions of light-years across. We have never observed a black hole anywhere near this size. A third objection is that the idea might simply be pushing the problem back a step. It offers an origin for our universe, but it immediately begs the question, what about the parent universe? Where did it come from? How did it get its laws of physics? This leads to a potential infinite regress, a chain of universes within universes. Some physicists are comfortable with that, but others argue it moves the idea into metaphysics, since we can never hope to observe these other universes. These objections are substantial. They highlight the gap between a compelling mathematical idea and a verifiable scientific theory. For the black hole universe hypothesis to gain wider acceptance, proponents must develop it further. They need to show how such massive black holes could form and, most importantly, derive concrete, observable consequences we can test. Without that progress, it risks remaining a fascinating but speculative footnote in cosmology. Science demands evidence, and for now, the evidence for this beautiful idea remains elusive. Let's pause and consider what it would actually, feel like to live inside a black hole. The answer, surprisingly, is nothing special. If our universe is the interior of a black hole, we wouldn't see cosmic prison bars or a giant wall at the edge of space. Our experience of reality would be exactly as we observe it. We would measure the laws of physics, observe the expansion of space, and see galaxies receding from us, just as we do now. The event horizon of our parent black hole wouldn't be a physical boundary we could visit. Instead, it would correspond to the cosmological horizon, the furthest we can possibly see due to the finite age and speed of light. It's an information boundary, not a brick wall. This is a key point that comes directly from Einstein's theory of relativity. Your experience of space-time is relative to your frame of reference. For an imaginary observer in the parent universe, our entire cosmic history, from the Big Bang to the distant future, would unfold within their black hole. They might see our universe's formation as a star collapsing and winking out of their sight. But for us, on the inside, space-time is configured differently. Our space is expanding and our time is ticking forward. The singularity isn't a place in space we're falling toward. It was a moment in time that we're expanding from. The Big Bang itself. The two perspectives are both valid descriptions of the same underlying reality. This dual perspective highlights the profound weirdness of gravity and space-time at their extremes. It suggests that what one observer calls a black hole, another might call a universe. This idea isn't just a quirky feature of this specific model. It's a theme that runs through modern physics, known as holography and duality. These concepts propose that two very different-looking physical theories can be mathematically equivalent, like two different languages describing the same world. A theory of gravity in a higher dimensional space can be equivalent to a quantum theory without gravity in a lower dimensional space. The universe in a black hole idea is a cosmological application of this kind of thinking. So the next time you feel a bit trapped by your daily routine, you can, take a moment to ponder this cosmic irony. If we are in a black hole, we are in a sense trapped. We can never leave our universe to visit the parent cosmos. Yet, within our cosmic prison, we have a space so vast it is practically infinite to us, filled with more galaxies than we can ever hope to count, let alone visit. It's a confinement on the grandest scale imaginable, yet one that provides more than enough room for the entire drama of cosmic evolution to play out. Birth of stars, emergence of life, consciousness. In the end, we stand at a crossroads of knowledge. The idea that our universe might be the interior of a black hole is not a proven fact. It remains a speculative yet deeply compelling piece of theoretical physics. It may turn out to be completely wrong. The standard model of cosmology, inflation, dark energy might be closer to the truth. Or, the correct answer might be something stranger than we can currently conceive. But whether the hypothesis is ultimately right or wrong is, in some ways, not the most important part of the story. The true value lies in the questions it forces us to ask and the new pathways it opens for science. This idea serves as a powerful bridge. Cosmology, the study of the universe's structure, quantum mechanics, the fundamental nature of matter and energy. It suggests that the birth of a cosmos might not be a unique metaphysical event, but a recurring physical process, like the birth of a star. By exploring this connection, physicists develop new mathematical tools, gravity, quantum theory, a quest that represents the holy grail of modern physics. Even if this specific path leads to a dead end, the exploration itself illuminates the surrounding landscape. This is how science advances. It doesn't proceed in a straight line, but by proposing bold, imaginative ideas and then rigorously testing them against observation and logic. Enjoyed this video? Like, comment, and subscribe.